This is CBS Eye on the World. I'm John Batchelor. I welcome Professor Dante Lauretta, University of Arizona, most importantly, the author of a new book, Asteroid Hunter, a scientist's journey to the dawn of our solar system. Professor, congratulations. This is wonderful, but we get in a time machine and go to February of 2004, a clear day in Arizona. You are an assistant professor at the time, looking forward to tenure, and your good friend and boss, Mike Drake, calls you on your mobile phone and says, come on over here to the Arizona Inn and meet Steve Price from Lockheed. That day begins a journey that we're just now illustrating in your new book. So who was Steve Price? Who was Mike Drake? And what did you learn that day? Good evening to you.
Thank you, John. I'm thrilled to be here. Mike Drake was the director of the Lunar and Planetary Laboratory at the University of Arizona, and he was the one who hired me at that point about 3 years ago onto the faculty here. LPL was founded by Gerard Kuiper, famous planetary scientist, really founded the field and was heavily involved in the Surveyor and Apollo programs at the dawn of the American space age. And the Lunar and Planetary Laboratory has been a training ground for young planetary scientists throughout that time. So Mike and I were both cosmochemists, that is, chemists who study material from outer space, lunar samples, meteorites, comet dust, and we had bonded quite a bit over those 3 years because of our shared scientific interest, and our personalities just really clicked. And he had taken me under his wing, and he was my mentor and my dear friend. And Steve Price was from Lockheed Martin, and he was the director of business development, and recently had worked with LPL to win a mission called the Phoenix Mars Lander, which had been awarded that year in 2004. And Steve was there to recruit Mike to be the principal investigator, which is the person in charge of these NASA missions, has full authority for the scientific integrity, as well as managing the resources to deliver to the agency. And Steve wanted to bring Mike and the University of Arizona back to the table with Lockheed Martin to go after a new mission, Asteroid Sample Return.
Asteroid Sample Return. At this point, to your knowledge, and you were halfway this, halfway that, but you knew everything about the NASA missions. Was there a comparable mission underway at that moment? Did you talk about it?
Yes, the Japanese Aerospace Exploration Agency was developing and flying Hayabusa, their first attempt to retrieve a sample from an asteroid. And that was in flight to their target asteroid, Itokawa.
So it was in the air. Let us begin with Dante Lauretta as a young man in the desert where you grew up, a man from the desert, in the desert, always thinking desert. It's a lively place, and apparently you have a favorite rock in the desert, so I imagine you sitting at your favorite rock, imagining your future. And from there, you went to the University of Arizona. When did NASA become part of your imagination, Dante?
When I was a senior at the University of Arizona in the fall of 1992, I was pretty directionless. I'd been wandering around, going to concerts, backpacking, hiking around the deserts and the mountains all over the Southwest of the United States. But I was looking for something, for a spark, for a direction, and getting a little worried because it was last year of school and I didn't really have any idea what I was going to do when I graduated college. And then I got a newspaper, the student newspaper, the Arizona Daily Wildcat, and there was a job ad, full page, that said work for NASA. And that just lit my imagination. It seemed impossible. NASA was the best of the best, where the geniuses worked, and they launched these fantastic missions of exploration. And I honestly didn't think I was good enough to do something like that. But I was so excited that I worked hard on that job application and luckily got that undergraduate research position. It seemed like the coolest thing in the world at the time.
You're in the Looney Lab right now at the University of Arizona. I believe you write in your book, and it's extremely well written and autobiographical. You didn't know the Looney Lab existed your 4 years at Arizona. Did they hide it? Is it behind a security screen?
Yeah, it's an interesting department. So we are, as far as I know, the only department of planetary sciences, strictly focused on planetary sciences. Usually we're stuck in with the astronomy or the geology departments. So when we focus on our PhD program, that's our primary educational activity, is training graduate students to be future scientific researchers in planetary science. We offer a few general education courses, but those are taken by non-science majors typically. So I was a physics major, math major. I had all of my science requirements and then some. So I never needed to look at the general education classes, and I wasn't a PhD student. So the planetary sciences program really wasn't very obvious on campus in those days.
You have a better idea. You and Mike are going to go to an asteroid. You don't know what asteroid. The idea is a sample return. Hayabusa's en route, so there's no failure to talk about. There's only dreams. And Lockheed presents this mission. However, we now have, and Dante's book is wonderful, for everyone listening who wants to go to the stars, NASA has guidelines, and those guidelines must be met, spending money preciously. And Dante's book is a wonderful example of try, and try again. Rejection makes you better. So in July of 2004, you submit your first proposal for a sample return mission, and it's rejected. However, I credit you and Mike. It just made you redouble your efforts. You just went back in. And do I say that correctly, that you were not disappointed? You took the criticism from NASA and rebuilt?
Yeah, it was an eye-opener for sure. We thought we had a great proposal and it was very strong, and it got the lowest ranking NASA can give a concept like this, what we call Category 4, which I won't mince words. It was a gut punch. You hope you put something credible forward. So when you get something like that, it really makes you think. And what we recognized right away was we were both pretty green. Mike and I were laboratory scientists. Mike had been running the laboratory, which had been leading a lot of these space missions, but he had been the administrator working with the university and so on, not actually in the trenches building hardware or flying these programs. And so we knew we had the skill set around us and that we could move this forward. But I think the most important thing was it felt really good. The team felt great. There was this energy where you start to become part of something much bigger than yourself. And if you've never experienced that, it's hard to explain, but you get this sense of this momentum that's kind of behind you, and it's just pushing you forward, and you want to ride it and see where it's going to take you.
In November 2006, there's a NASA program called, there's a NASA competition, and you enter into it. You're versus Grail, which is an Earth mission, I believe. You're versus Vesper, that's a Venus mission. And you've got a mission now to a place in the universe. What is 1999 RQ-36?
Yes. Whenever a new asteroid is discovered, it immediately gets a catalog number. And the first 4 digits are the year. So 1999 RQ-36 is an asteroid that was discovered in 1999. And then the RQ-36 is a counter. It starts out with A, goes through Z, and then it goes to AA, and then AA1. So you can get a sense of how many asteroids were being discovered in that time frame. So RQ-36 tells you it was several hundred asteroids down the list of what was discovered that year.
The identification of that asteroid gives the application to NASA great weight. But there are other things that have to be dealt with, like the competition with other missions. NASA's only going to fund one of these missions, maybe. And in December of 2007, Dante, Lauretta, Mike Drake, and the whole team that have worked for years are rejected. When we come back, what next? The book is Asteroid Hunter, a scientist's journey to the dawn of our solar system. Dante S. Lauretta, professor at the University of Arizona, is the author. It's autobiographical. It's extremely helpful to understand the steps that NASA requires for a successful mission. Even a mission that is only partially successful has to go through all these steps. 2 rejections. And now Mike Drake in the lead. And it's important to say Mike's job was management. There's science, there's engineering, there's cost, there's management. And Mike is a terrific manager. And leaves Dante at the time for the science and to put together the science team. You put together After that December 2007 gut punch, I guess this is a shot to the head, you put together yet another program going forward, and you've come up with a wonderful name. How did you do that?
When Mike brought me on, that was the direction that he gave me. He said, Dante, go define the scientific objectives for an asteroid sample return mission. So I went home that night and I started thinking about the different communities that are interested in asteroids. And I started with the group that I'm most familiar with, the cosmochemists and the astrobiologists that are looking for signs of the seeds of life. How did Earth become a habitable world? How did the organic molecules that make up all the biological organisms on our planet, how did they get here? Because our models of planetary formation suggest the Earth was very hot and very dry when it formed. And those compounds were probably delivered later from objects that formed in the outer solar system where ices are stable and organic molecules are stable. So that was our origins, and the O for OSIRIS-REx. And then I thought about the astronomers. There's a large community that they spend their time on mountaintops, not so much anymore because it's gone to remote operations, and I think they kind of miss it, but they used to stay up on the mountains all night long, scanning the skies for asteroids, looking for ones on collision courses with the Earth, and generally just developing an overall survey of our solar system. And then resources. In situ resource utilization is a pretty lively community, very adventurous, very forward-thinking. The idea is, can you extract resources from objects in space instead of launching them off the surface of the Earth? You could maybe make fuel, you could make structures, you might even be able to extract economically valuable minerals like platinum group elements. And then finally, security. That is what Congress is most interested in when they fund NASA. And what I find intriguing is when there's surveys of the general public in terms of what should be NASA priorities, asteroid impact hazard identification and mitigation is always at the top of the list. So a lot of people think about asteroids as potential natural disasters, which they are, and something that we can do something about. So I had 4 letters, O, S, R, and S, and I was looking for a cool name. And I said, oh, all I need to do is just buy a couple vowels, slide them in between the first S and then after the R, and get Osiris, who's an Egyptian deity known for being the god of agriculture and life, like asteroids, but also the god of the afterlife and the underworld. So he has this dual nature, bringer of life and harbinger of death, and asteroids have that as well. When we got to the 2007 competition, we were moving up a category. The reason we lost in 2007 was we were too expensive for that program. And then a new program was coming online called New Frontiers with a bigger budget. So I needed to be bigger and stronger. A teammate threw out OSIRIS-REx, which we thought was hilarious. And then I went home and I thought about it and I was like, okay, that sounds really cool. We got to have that as the mission name. And so Rex is the regolith explorer. Regolith is the blanket of loose rock and dust on these airless bodies. And we're explorers. And I thought it was cool that we'd have a noun at the end of our acronym. And the OSIRIS-REx mission was born.
May 25th, 2011. NASA says yes. Tragedy follows, the loss of Mike Drake. And you visit him in the hospital and he says, your mitigation. What does that mean, Dante?
Well, a lot of what you do with these missions is mitigate risk, because you're constantly thinking about all the things that might go wrong, of which there are numerous, and how do you make sure you're resilient against those failures? Belt and suspenders is the philosophy. You usually have 2 paths to anything that's critical for the program. And when Mike was in the hospital, he had been ill for a while, over a year. And so it wasn't that unusual, but this was a particularly dire surgery that he was going into. And the survival rate, which I researched, was very low. And I was heartbroken as soon as I saw that. And I wanted to know, what was the plan? How were we going to go forward without him on the program? He was our leader. He was the visionary. He was my mentor, my friend, and our rock, really. He always provided that grounding for us to keep moving forward. Whenever I doubted, Mike was the one that lifted me up and said, we can keep doing this. We can keep going forward. Don't give up. And so I said, Mike, this is a red risk. Red risks are the most serious challenges missions face. Usually it's a flag up to headquarters that you can't solve this problem alone. You're going to need more time, more money, more people, something to solve the problem. And Mike just looked at me and he said, "You, Dante, are the risk mitigation," meaning that he was looking to me to carry the program as its leader into the future.
One more review before we put the booster together with the satellite and we launch. The review is in, I believe it's in 2014, May of 2014. Correct me if I'm wrong, Professor. And NASA tells you everything that's wrong. And you're sitting there thinking, we're going to be rejected again. And then they said yes. What convinced them, Dante?
Yeah, that was our confirmation review. And that's a really important gate. So when you get selected, which is what happened in 2011, NASA gives you a few $1 million to develop your design, what they call the preliminary design, where it looks credible and you can really estimate what it's going to cost. And the confirmation review is where they say, okay, we understand your costs and we're going to guarantee this level of support at hundreds of millions of dollars in value. And yeah, so that's where it's make or break. You can be canceled at that point. And we were worried about that. First of all, because we had some technical challenges, but also there's politics going on in the background and people are trying to redirect this funding line to their program. And the biggest challenge we faced was getting the spacecraft safely down to the asteroid's surface. And we needed a guidance system to do that. And they just clobbered us on the design that we had there. It was new, it was innovative. The hardware provider hadn't built flight units for NASA before, which is a very rigorous activity. And so they were worried. It was a major weakness. And that might be something that could get you canceled. But they thought everything else was really strong. The science was very compelling. Overall, the spacecraft engineering design was solid. The costs were very well understood. And this is something that we focused on a lot to make sure we were cost credible. And they knew we could solve the problem. It wasn't an unsolvable one, but they directed us to come up with a backup solution. In case the primary mechanism failed, you still needed to be able to get the spacecraft down to the surface. And that was the key finding from that confirmation review.
We need to get to Bennu. It's summer of 2016. The launch is successful. Dante goes through a lot of anxiety and it works. The Bennu, OSIRIS-REx is on the way. It's going to be some years, more than a year now. So when we come back, we're going to arrive at Bennu and talk about the plan A, plan B for sample return. Dante Lauretta is the book's author, a professor at University of Arizona. The book is Asteroid Hunter. We're now in space. The asteroid Bennu is approaching perihelion, meaning that it's close to the sun. The perfectly built OSIRIS-REx spacecraft has approached it over a time period in which they count out at the Mike Drake building in Arizona. They count each day, 438, 437, 436. Well, it's just days left. And we're now accompanying Bennu. However, there are surprises. And one surprise is there's no beach. What beach, Professor? What were you looking for?
Yeah, we mentioned that we discovered the asteroid in 1999, and it comes close to the Earth every 6 years. So in 2005, when we selected it as our target, we performed an unprecedented telescopic astronomical campaign. And two key instruments that we used were the Arecibo planetary radar system, which was based in Puerto Rico, and the Spitzer Space Telescope, which is part of NASA's Great Observatories program. Both of those suggested the average size of particles on the surface of the asteroid was smaller than an inch or so. And when you have two pieces of information that give you the same conclusion, you start to build a lot of scientific confidence. And we thought that meant it was going to be gravelly or sandy on the surface and very easy to pick up particles. So when we talked about those reviews in front of NASA, I got up there and presented all the data, made this convincing case that the surface was beach-like. I told it to my team. I told it to the public. I must have said it 1,000 times before we got to the asteroid. And then we get there and we see this rough and rugged and rocky boulder-strewn surface, which looks quite daunting to send this beautifully crafted spacecraft down to collect a sample from.
Yes, it's spheroid, but it's not perfectly round. There are pictures of it in Dante's book, and you get an understanding that it looks like one great big gravel pile. That might be what it is, but it has gravity. What'd you say, 1/5 millionth of the Earth's gravity, something like that?
That's correct. About the same as the astronauts on the International Space Station experience.
However, that means that this loose collection of rubble uh, isn't anything you can land on. You have to tag it. So now we come to the invention of inventions. The engineering in your journey is spectacular. I've learned that at all space engineering. There is no such thing as, no, we can't do it. It's, we'll find a way. Okay, tell us what you want. Your engineer's magnificent. Let's go right to the end. What is laser tag, TAGSAM? What is that referring to, Dante?
Right. So TAG is an acronym for touch and go. As we discussed, the surface is rubbly and it's really fluid-like. And we learned that especially during the sample collection event itself. So we want to fly down to the surface, kind of like a scuba diver moving around a coral reef is a good way to think about how you can move around these objects. Just place our sample collection device called the TAGSAM, which is the touch and go sample acquisition mechanism. It's basically like an air filter that we push onto the surface and then almost like a leaf blower action, just shoot gas into the gravel and push it into that filter. But the challenge is getting to a safe location. Because there's so many large boulders, there's very few flat patches that have those small particles like we planned on picking up. So we had originally used a laser system, which is like a laser pointer. You fire the laser, you could measure how long it takes to hit the asteroid and come back to your spacecraft. We know the speed of light, so you know how far away you are. And the laser was going to give us information as we were approaching the surface. Were we coming down at the right speed? And were we coming down at a relatively constant rate? And so it was there as a safety check for the final closure with the asteroid surface.
Yes, now there are concerns here in all directions, but I want to focus on one, which is, what is the surface made of? The science. We've spent a lot of time with engineering and with management, but the science is everything here. And Dante is an astrobiologist along with everything else as a chemist. So what science are you looking for that would help move the story of, did asteroids deliver water? Did asteroids deliver the spark of life? Does that mean there's spark of life everywhere? How does the chemistry work, Professor?
Yeah, the reason we chose our asteroid, which we ultimately named Bennu to get rid of that catalog number, make it more of a destination, because it was so dark. That's what got our attention right away. It's one of the darkest objects in the solar system, reflecting a little over 4% of the sunlight that hits its surface. It's like a lump of coal. And we took that darkness to infer that it probably is loaded up in carbon. And carbon is the central element to all life on Earth. It's one of those elements that we thought would have been very rare when the Earth was forming in the inner solar system and would have had to have been delivered to our planet from outer reaches of our system. And so that got us excited right away. We had a couple of instruments that could measure the chemistry and minerals that are on the surface. They're called spectrometers, and they look at wavelengths of light. And there's certain areas where minerals will absorb light, and that gives you a little fingerprint for what's on the surface. Not only did we find the carbon, it looked like Bennu was loaded up in organic molecules and also carbon in minerals called carbonates, but we saw abundant signs of water. And that's really interesting because it's a small body. It has no atmosphere. Liquid water is not stable. Even ice is not stable. It would be more like a comet if that were the case. But this water is locked up in minerals called clays, which can hold the water in their structure and resist releasing it even at the high temperatures of the inner solar system.
I mentioned that it's a loose rubble pile. Well, that has been a concern for some months now because there they are going in. But the image I like, Dante, that you use is that Bennu pops like popcorn. What does that mean?
One of the big surprises, and there were many, I call Bennu the trickster because in this case, it was literally throwing curveballs at us. We went into orbit on New Year's Eve of 2018, rang in the new year in our tuxedos and everything by putting a spacecraft into orbit around this small asteroid. And less than 1 week later, we were just taking routine navigation images and we saw an explosion off the asteroid's surface. And it looked like this crazy dynamical event. And we thought, we're in trouble. This is hazards. We could damage the spacecraft. all of a sudden you're in this emergency contingency mode, evaluating scenarios. What are you going to do? Do we need to leave orbit? Do we need to get away from the asteroid? And this is where microgravity really messed with our minds, because these were not very energetic events. It doesn't take a lot of energy to kick off rocks. We saw things the size of golf balls, the size of softballs, maybe even the size of basketballs leaping off the surface of this asteroid. And it turns out this is a very common phenomenon. Every day we saw at least one particle come off, sometimes a whole spray of them. They would bounce off the surface. They would go into orbit. Some of them would leave and become part of the interplanetary dust population. So it was a stunning discovery. It's what we call an active asteroid. It's shedding material, losing mass, kind of like very low-level cometary activity.
Dante now sets the team a challenge. Find me something to land on somewhere on the surface. And what begins weeks of Dante not sleeping because he's been staying up studying. He needs better and better photographs. Everybody does. First, the team takes the site team, and then he asks the public to help. They're looking for something to land where it has to be safe. You have to be able to deliver the sample collector to it. It has to be safe, and also it has to have some science to it. It has to be something you want to sample. And at this point, I figured there was going to be a crash and the book would end with a catastrophe. Except that I know that it was successful and it came back. That's the thing. I find that the anxiety here is very high. It comes through the pages. I can see day after day in the Drake building. What are we going to do today? Worry. That's what we're going to do. But you come down, the Sweet 16, the final, the Elite 8, and then the final 4. Let's go to the final 4. You name them for birds: osprey, nightingale, sandpiper, and one more.
Kingfisher.
Thank you. Kingfisher. And everything has an advantage. I remember this debate. It was in the news every day. And my colleague and I were saying, well, sandpiper looks pretty good. But then again, and how did you choose, Dante?
Yeah, it was chaos early on. We didn't have a good series of quantitative metrics. We were kind of going with our gut. I think we had gotten a little complacent with the beach idea. We didn't think it was going to be that big of a challenge. The engineers had come up with an algorithm that could just feed into the shape model of the asteroid and it would kick out the safest place to go and get your sample. And that is not at all what it was. The surface is so rugged, it's hard to imagine. I talk about exploring it in virtual 3D. It's like being in an abandoned city with these skyscrapers everywhere. These giant boulders just tower everywhere. And we have to precision park the spacecraft. So the first thing we had to do was replace that laser tag with what we call bullseye tag. We had to upgrade the flight software to make the spacecraft smarter so that it could actively guide itself away from hazards and towards a safe area. And what did safe mean? It needed to be relatively flat. We were really worried about coming down on a slope and tipping the spacecraft over and crashing into the surface. This is what the first Hayabusa mission did. And we had watched that play out. We had watched our colleagues crash land on the surface of an asteroid and seen the failure real time. So we were very cognizant of the fact that you could lose the sample if you didn't get it right. So then we needed it not only to be flat, but we needed small particles, those gravelly particles that we talked about, to pick up. And Bennu didn't have areas that were both flat and had small particles. It was either one or the other. And so that was what we were really debating. How much risk could we take to get into the sampleable area? And if we wanted to be the most scientifically valuable, that would maybe even add a little more risk at the sake of increasing the scientific return of the program.
The choice is Nightingale. It's got a boulder, Mount Doom, I think. It's got risks. However, not to be unfair, the machinery, the engineering is magnificent. It does this automatically. It's like Tesla, 1,000,000 miles away, backing in and pulling out a sample. And
200 million miles away.
Thank you. 200 million miles away. Well, the little Tesla robot that Lockheed built and the engineering adjustments with your team are magnificent. So is all of the camera preparation. And you wind up with a sample that's too much. You're pulling it as, he doesn't mean just trickster. He means like, you think you're confident. here's this one. And this one is too much sample. You're leaking.
That's right. Yeah, the surface response was completely unexpected. So we thought we were going to touch down on a rock, something hard, like touching down on the ground on Earth or on the moon or Mars. It wasn't like that at all. It really behaves very much like a fluid. So as soon as the sample collector, the TAGSAM, touched the surface of Bennu, it just continued to plow in. It was like jumping into a pool of water. And as a result, the sample head was filled all the way to the brim with material. And imagine you're trying to carry a bucket of water that's filled all the way to the top, and you're trying to carry it down a mountainside. Every little motion is going to cause slosh, and that's exactly what we were seeing. Sample was just flowing out of this collector. It was heartbreaking and terrifying. After years, at that point, we had been working 16 years to get to that sample. All of those challenges had been overcome. We got to the surface, we got material, we take our first look, and we're losing it into space.
However, the OSIRIS-REx craft is so sturdy and it's so reliable, it's going to return to Earth. And when we come back, there's more tricks coming. Just because you leave Bennu behind you doesn't mean that you're going to get everything smooth. Dante Lauretta is the author, professor at the University of Arizona. The Asteroid Hunter is the book, A Scientist's Journey to the Dawn of Our Solar System. We're waiting for the re-entry of the sample collection. It's going to re-enter like the early days of the Apollo program. You'll see a chute open and it'll drift down and you'll pick it up just perfectly. You know, the Navy SEALs will go over the edge of the helicopter. Everybody will be happy. Well, Dante, you're out there in helicopters chasing this, except for instead of the ocean, you're using your desert, the desert you're so familiar with. And everything is going according to plan. OSIRIS-REx drops off the sample return. It blazes through the atmosphere. Its heat shields work. And then where's the drogue chute? What happens?
Right. At that moment, I'm in a helicopter and we're heading out to the Utah Test and Training Range, which is a Department of Defense facility. That's the largest continuously controlled airspace in the continental United States. So it's a nice place to bring in a capsule from outer space. And it's a wide open salt flat out there. So plenty of flat ground to land on. And I know down to the second when these events are supposed to occur. And after we go through the hypersonic regime, a small parachute called a drogue chute is supposed to come out and stabilize the capsule's flight as it transitions into the subsonic regime. That's supposed to happen at 100,000 feet of altitude. And all I can do is listen. I've got my headphones on. I'm in the back seat of the helicopter, and I can hear the range control officer reading out the different status points. And they say, crossing through 100,000 feet. And I'm waiting for drogue chute spotted, and they don't say anything. And there's an Air Force officer in the front seat, and I tap her shoulder and I'm like, drogue? She's like, they're not calling drogue. And at that point, my heart just sinks. And I flash back at that point, almost 20 years to a very similar capsule that crash landed in that same Utah desert called the Genesis mission, where the parachute failed to deploy. And NASA's there with cameras. We're doing a live TV broadcast. And I'm starting to think about, how am I going to keep it together in front of the world with my heart broken and this mission a disaster in the Utah desert? 3 minutes go by and we're crossing through 60,000 feet, and I'm just desperate and everything is going wrong. My heart is pounding. And then finally, like a miracle, I hear main chute spotted. And I just break into tears. I'm so overwhelmed with gratitude and thankfulness. And at that point, I know we did it. We crossed the finish line. We got the sample back to the Earth. Mission success.
There's a photograph of Dante, and he looks extremely collected when he's kneeling down to the sample site. So he recovers that day, and the sample is spectacular. I note that OSIRIS-REx goes on to another mission, and you hand over the PI position to your colleague, Danny Della Justina. I hope I say that correctly.
Yes.
Where is OSIRIS-REx now? Where's it headed, Dante?
Yeah, so Danny Della Justina is someone who I met in 2005 when she took my 1-credit seminar on asteroids and meteorites at the University of Arizona. And we bonded immediately, kind of like siblings, and we've been working together almost ever since then. And she's risen up through the ranks. She's now an assistant professor, just like I was in those days when I got that phone call from Mike Drake here at the Looney Lab, the Lunar and Planetary Laboratory at U of A. And she is the principal investigator for OSIRIS-REx. We've rebranded it as the Apophis Explorer, and it's on its way to rendezvous and orbit another near-Earth asteroid. It can't collect a sample. All that hardware is on Earth now, but it still has all those great cameras and spectrometers and the lasers. So we're going to do a fantastic mapping campaign and interact with the asteroid's surface. And I think the thing I'm most proud of is it really carries Mike Drake's vision forward of training the next generation and building these leaders that can go off and do amazing things in the future.
Yes, and you mentioned in the close of your book, there are 200 students or 200 people who were affected by this, and that's 2 generations on, Professor, not just one.
That's right. Yeah, well, I think one of the best parts about having a university lead these kinds of NASA programs is you get access to all this enormous young talent. And they're so excited and so enthusiastic. It's a dream come true for them to work on a NASA mission like this. And so you really get the best of the best. It was our primary recruitment tool. Over 20 years, we hired dozens of our students onto the mission as scientists, engineers, managers, artists, all of the skill set you need to make a mission like this a success.
Dr. Dante Lauretta, Regents Professor of Planetary Science and Cosmochemistry in the Lunar and Planetary Laboratory and the Department of Planetary Sciences at the University of Arizona. The book is The Asteroid Hunter, that's Dante, A Scientist's Journey to the Dawn of Our Solar System, a Success. I'm John Batchelor.